All right, so hello everyone. Welcome back to the fourth section and the second example for this series of video tutorial. And we're going to be working on a problem that is very similar to the section O2. So we're going to be looking at a active shape morphing truss. So that's just like what we've done in the section O2. But the things we're going to be doing here is we would spend more time on the nonlinear solver, and we're going to actually use two solvers, a Newton-Raphson solver for the loading and also for the self-actuation. So this type of active truss is kind of quite common, and you might be able to see it being used for aerospace, robotics, so on and so forth. So the red bars are those active trusses. So here we're going to be looking at a thermally actuated truss. So this thing has a thermal expansion coefficient alpha of about 0.001 strain per Kelvin temperature. And we assume that we're going to heat it up by 30 Kelvin. So typically when you're working with this type of systems, the active truss Young's modulus are going to be smaller than those from the normal truss. So that's reflected in these property definitions. So we are assuming that for our normal trusses, it's going to be 2 gigapascal. So that's a value that's quite common for many of the normal plastic and wood materials in that range, paper around that range. And then for the active trusses, we're gonna decrease the value by 1,000, so it's 2 megapascal. It's going to be a very soft truss. We assume that the cross-section areas are the same for the two. And let's try to code the system and see what's happening. All right. So the classes here for this example would be actually identical to what we have in the section 2. So let me actually show you that by opening up, first of all, this is the assembly truss from example 2 on the right. And let's go to the assembly truss for my section O2, so the previous section. So you can see they are identical. So the solve fk function is the same, and then the initialize is the same. So they both have a bar element that's the non-active conventional bars, and also active bar elements as part of the assembly. So going back to section number 4, I don't need these. And this is also a figure just to compare these assembly from the previous examples, the example 1 with what we're looking at here. So in the previous example 1, so basically section 3, we are dealing with the traditional truss, right? So there's no active bar, and therefore the solve fk function is just to find the like the global force and the global stiffness from the bar element and then just return it. But this time, if you look at that solve fk function on the right, it has two components, two type of element. So they both produce a global force and a global stiffness matrix, and we need to sum them before we return it. That's the only difference here. So later in the next 3 sections, I will be talking about how the bar elements are formulated, how to achieve the stiffness matrix and global force vector assembly, and then also talked a little bit more about the Newton-Raphson solver for nonlinear problem. It's implicit solver. So that's the theory part, but without going too deep, that's actually just focus on this example to see what we can achieve once we have those theory ready and being organized in a code package. So again, this is to define all the objects like the node bars, active bars, and turn that into a assembly. So if you're working, let's say if you eventually get a job working for COMSO, ANSYS, or Abacus, you would have very similar, um, 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 if you need to adding like a new element you developed during a PhD, You well, of course, first of all, you would be coding in C++, not in MATLAB, but then C++, different from the difference between C and C++ is just that C++ gives you better object-oriented programming support, and that's what you need to use when trying to insert your new elements into basically the all the code that the company has already created, right? So you will see something very similar there. But anyway, let's keep moving. So for these design, the nodal coordinates are actually going to be very straightforward. We've already done that actually. So the fourth node are the fourth corner. This one is the fifth node. It's at the center. So if we want to see it, I've already actually generated this solution. But oh, I don't think I've added the source code. So make sure, oh, I've already added it. So I'm probably in the wrong folder. There we are. That will fix the problem. Okay, yep. Make sure the current folder is where we can find the right assembly truss class for this case. So, all right, let's take a look. Yeah, indeed, the five nodes, they are at the places where we want them to be. And again, if you want to change these view angles, you are able to do that. And if you change the view angles, you would be able to look at the system from a different perspective. If you change that ranges, so for instance, if I let's say here is from negative 0.5 to 1.5, if I want it to be 2 and negative 1, I'm able to do that. And the figure, you can see that now the axis range is from negative 1 to 2. So let's get it back to what it used to be. All right. So after that, we define the active truss, the connectivity. So node 1, 3 is the first active truss, 2, 4 is the second, and then the traditional truss or the common truss without self-actuation, 1, 2, 2, 5, 1, 5, 3, 5, 4, 5, and 3, 4. Right, those are the primary ones. And then we set up the Young's modulus and the cross-section area for those bars. So I have 6 conventional bars or conventional trusses. That's why this is a 6x1 vector. And I have 2 active bars or active trusses. So that's why this is a 2x1 vector. So ones, 2, 1, that will create a 2x1 vector, whereas ones, 6, 1, and just in case you've never seen these, in MATLAB, it's going to give you a 6x1 vector. All right, so that's what will happen. And let's move on to the Newton-Raphson solver. And this first solver we're going to be using is to apply these heating or these heating-induced strain and also changing the original length in the element. So what will happen is we create these solver nonlinear truss action solver, and that's the one we can use to capture this type of behaviors. It's using the Newton-Raphson type of philosophy, but instead of dealing with the applied load, this time we break that applied heating-induced strain and length change into multiple steps. And so for that equilibrium after, let's say we change the stress-free length of the bar from 1 meter to 0.9 to 0.8 and to 0.7. So that's how we do it. And the support, node 1 and node 2, they're fully restricted in all 3 dimensions in the 3D space. And then 3, 4, 5, they are restricted in the Y direction, but they're free to move in the X and Z direction. So that's how the supports are defined. So the target length, so here we're trying to address the target length of that active bar element. We only apply the actuation to the first bar. So that's the left one, 1, 3. And so this is how we get the target length. We have delta string, which is basically how much strain changes are induced by the setup. It's going to be the delta T times your alpha. And we assume that heating things up will make it contract. So it's going to be times the original length times 1 minus delta strain. That's a very crude, simple computation, but it will get us to the ballpark. So basically, for a system like this. So we will be breaking up everything into 10 steps, but this time for the target L, this is our final target. So the algorithm will automatically break things into 10 steps and finish the calculation for us. And again, the maximum iteration is still set to be 30. So when playing with these nonlinear solvers, it's sometimes you might run into a lot of numerical issues. So it does take some trial and error to figure out what's the best setup for these parameters. So in a way, it's really like machine learning, parameter tuning in machine learning. I don't know if you've done that before, but sometimes it's not very intuitive because mathematically, I don't know if you're aware of this, but Newton-Raphson method, the Newton's method itself, the convergence of that Newton's method is still an unknown problem. So the mathematicians still have not yet come up with a robust criterion to judge how the Newton's method will give you a converged result. So because of that, that's why we have to play with the parameter here and there. But over time, you actually get used to it once you've run the code for many times. But anyway, with that, we are actually able to start running the system, and let's see what we get. So I want to stop here. And here we are. So we have achieved a little bit of contraction on the left. It starts twisting this upper triangle, push it towards the left side. The rotation is not very large, but it's still there. So this is what exactly we hope to happen. So let's assume that on top of that applied heat, that say I still want to add another 20 Newton forces at the left node. Well, how could we do it? So this example is also here to show you how we can actually stack two different solvers and to try to figure out the combined effect of a sequence of action you want to put onto these active structures. So here we create this solver Newton-Raphson loading. So this is a loading solver that's a little bit different from the Truss action solver. And we still do the same thing. We set the assembly to be part of the properties. We set up the support, which is just the same as the previous one. And this time, we've already learned the load from the Newton-Raphson loading solver. We put the two Newton of forces pointing downwards at node 3, and then we get 10 total incremental steps. So that will give us a total of 20 Newton forces here. And the maximum iteration is still 30. And after that, we just solve it, and let's just keep letting the system to run, right? This is 10 incremental steps. And actually in the previous one, it's also 10 incremental steps. You can see the how many iterations it requires to get to the final result. So typically 3 to 4, between 5 to 10 iterations might be that sweet spot. If you only have 2 iterations and you find the equilibrium, so perhaps what you can do is to get your increment less. So maybe instead of using 10 increment, I can use 5, and I have a little bit more iterations there. If it's unable to find the equilibrium after, let's say 30, so then in that situation you want to make more increment in your solution. All right, so this is what will happen if we further add this 20 Newton force up here. It will just keep pressing the system and deform it more towards that side. So hope that this gives you an idea of how you can directly stacked two systems on top of each other. So as long as you do not initialize the assembly in between the solvers, you can apply multiple solvers and get the sequence of motion. So um, if you're curious about what kind of solvers we currently have here, so these, if you go to the source code folder, so these are all the solver files that we can use to basically capture how these active structure change their shapes when you apply stimuli or when you apply loading onto them. So we will actually start talking about the Newton-Raphson method pretty soon in just a couple more sections. So, all right, so this is the fourth section here, and we're finishing up this example 2. So if we go back to the syllabus, you can see that in the next section, we'll actually start jumping into the theory section. So we will actually start to learn about the math and the mechanics behind all of these so that one day if you are going to be creating your own solver to or creating your own element to just attack a specific research problem for yourself, you would have the knowledge and you would know where to look for the knowledge. So section 5 would be central difference and bar element formulation. Section 6 is about stiffness matrix assembly. And then section 7 is the Newton-Raphson method, which we've already used 2 variations of that. So we'll get a little bit more insight into the theory behind it. And after that, we will have 2 more example sections. So hope that gives you a heads up about what's coming next. And with that, thank you very much for your attention. And I really hope that you will have a great rest of your day.